Power functions and polynomial functions. A square is cut out of cardboard with each side having length L. If we wanted to write a function for the area of the square with L as the input and the area as output, you may recall that the area of a rectangle can be found by multiplying the length times the width. Since our shape is a square, the length and the width are the same, giving the formula. A of L equals L times L equals L squared. Likewise, if we wanted a function for the volume of a cube with each side having some length L, you may recall volume of a rectangular box can be found by multiplying length by width by height, which are all equal for a cube, giving the formula V of L equals L times L times L equals L cubed. These two functions are examples of power functions. Functions that are some power of the variable. A power function is a function that can be represented in the form f of x equals x to the p power, where the base is a variable and the exponent p is a number. Example 1. Which of our toolkit functions are power functions? The constant and identity functions are power functions since they can be written as f of x equals x to the 0 power and f of x equals x to the first power, respectively. The quadratic and cubic functions are both power functions with whole number powers. F of x equals x squared and f of x equals x cubed. The reciprocal and reciprocal squared functions are both power functions with negative whole number powers since they can be written as f of x equals x to the negative first power and f of x equals x to the negative 2 power. The square and cube root functions are both power functions with fractional powers since they can be written as f of x equals x to the 1/2 power or f of x equals x to the 1/3 power. Characteristics of power functions. Shown to the right are the graphs of f of x equals x squared, f of x equals x to the 4th power, and f of x equals x to the 6th power. All even whole number powers. Notice that all these graphs have a fairly similar shape, very similar to the quadratic toolkit, but as the power increases, the graphs flatten somewhat near the origin and become steeper away from the origin. To describe the behavior as numbers become larger and larger, we use the idea of infinity. The symbol for positive infinity is infinity and negative infinity for negative infinity. When we say that x approaches infinity, which can be symbolically written as x approaches infinity, we are describing a behavior. We are saying that x is getting large in the positive direction. With the even power functions, as the x becomes large in either the positive or negative direction, the output values become very large positive numbers. Equivalently, we could describe this by saying that as x approaches positive or negative infinity, the f of x values approach positive infinity. In symbolic form, we could write as x approaches positive or negative infinity, f of x approaches infinity. Shown here are the graphs of f of x equals x cubed, f of x equals x to the 5th power, and f of x equals x to the 7th power, all odd whole number powers. Notice all these graphs look similar to the cubic toolkit, but again, as the power increases, the graphs flatten near the origin and become steeper away from the origin. For these odd power functions, as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x approaches positive infinity. In symbolic form, we write, as x approaches negative infinity, f of x approaches negative infinity, and as x approaches infinity, f of x approaches infinity. Long-run behavior. The behavior of the graph of a function as the input takes on large negative values, as x approaches negative infinity, and large positive values as x approaches infinity, is referred to as the long-run behavior of the function. Example 2. Describe the long-run behavior of the graph of f of x equals x to the 8th power. Since f of x equals x to the 8th power has a whole, even power, we would expect this function to behave somewhat like the quadratic function. As the input gets large positive or negative, we would expect the output to grow without bound in the positive direction. In symbolic form, as x approaches positive or negative infinity, f of x approaches infinity. Example 3. Describe the long-run behavior of the graph of f of x equals negative x to the 9th power. Since this function has a whole odd power, we would expect it to behave somewhat like the cubic function. The negative in front of the x to the 9th power will cause a vertical reflection, so as the inputs grow large positive, the outputs will grow large in the negative direction, and as the inputs grow large negative, the outputs will grow large in the positive direction. In symbolic form, for the long-run behavior, we would write, as x approaches infinity, f of x approaches negative infinity, and as x approaches negative infinity, f of x approaches infinity. You may use words or symbols to describe the long-run behavior of these functions. Polynomials. An oil pipeline burst in the Gulf of Mexico, causing an oil slick in a roughly circular shape. The slick is currently 24 miles in radius, but the radius is increasing by 8 miles each week. If we wanted to write a formula for the area covered by the oil slick, we could do so by composing two functions together. The first is a formula for the radius r of the spill, which depends on the number of weeks w that have passed. Hopefully, you recognize that this relationship is linear. R of w equals 24 plus 8w. We can combine this with the formula for the area A of a circle. A of r equals pi r squared. Composing these functions gives a formula for the area in terms of weeks. A of w equals A composed with r at w equals A of 24 plus 8w equals pi times 24 plus 8w squared. Multiplying this out gives the formula A of w equals 576 pi plus 384 pi w plus 64 pi w squared. This formula is an example of a polynomial. A polynomial is simply the sum of terms, each consisting of a vertically stretched or compressed power function with non-negative whole number power.